Today we're going to look at something which, for the purposes of this video, I'll call a physicist's favorite function. This is called also the Dirac delta function or the Dirac delta distribution. And often in like sketchy physics notes, you'll see it defined as follows. Delta x equals plus infinity where x equals 0, and 0 if x is not equal to 0, where this infinity is chosen so that if we take the integral from minus infinity to infinity of f of x times delta x dx, you get f evaluated at 0. So somehow this function has the ability of pulling out another function's value when you apply this integration action. Well, this is all very sketchy, and we would like to do this with a little bit more care. And I think probably if you were to look at those sketchy physics notes that I talked about before, you would see this little bit of more care happening on the next couple of pages. So after all, those sketchy physics notes were not really all that sketchy. Okay, so we're going to do this two different ways. One with a step function type object and another one with a continuous function. Okay, so let's set delta n of x equal to the following piecewise function, which we'll see is a step function. So it's going to be n as long as x is on the closed interval from 0 to 1 over n, and it'll be equal to 0 otherwise. Great. So let's get a bit of a picture of what's going on here. So let's say that's my axis, and let's go way up here and put n. And here we want to think that n is quite large. But if n is quite large, then 1 over n is quite small. We'll put that right here. Okay, and then what we have is that our function is equal to n if x is between 0 and 1 over n. So that means from here to here we have the following horizontal line, or we've got a continuous function. But then outside of this little interval here, the function is 0. So that means we'd have an open circle here, and then we would shade the real line back this way, and then we would have an open circle here, and we would shade the real line this way. Okay. And so now let's notice that under this setup we have delta x is equal, and I'll put this in quotes because this is a bit sketchy in itself, delta x is equal to the limit as n approaches infinity of delta n of x. Okay, nice. And the thing is that delta x itself doesn't really exist because this limit doesn't really take on a nice value. What does exist is the limit of the integral involving these objects, and it builds this exact thing right here. And that's what we'll see. Okay, so let's do this calculation. So I'm going to start here with my integral from minus infinity to infinity of f of x times delta x dx. And like I said, outside of the integral, this doesn't really make any sense, but inside the integral, it kind of makes a little bit more sense because we can define it in terms of that limit. Okay, so anyway, let's see. We'll have the limit as n approaches infinity. Now we'll have the integral from minus infinity to infinity of, let's see, we'll have f of x times delta nx dx. Okay, but now we'll use this fact, the fact that we've got a step function for our delta n. So let's see, that's going to allow us to rewrite this as follows. We have the limit as n goes to infinity, and then we'll have n times the integral from 0 to 1 over n of f of x dx. So let's see how we got there. So delta n of x is equal to n when x is between 0 and 1 and 0 otherwise. That means since it's 0 otherwise, that will collapse this infinite integral into the integral from 0 to 1 over n. but then it's equal to a constant there, which we can clearly factor out of the integral. Now we're going to do integration by parts, and this will give us some sort of simplifying effect. There are a couple of ways to do this, but I think maybe this integration by parts method, even though it's maybe not quite as careful as the other methods, requires us not to have to go into something like the mean value theorem for integrals or so on and so forth. Okay, so what we'll use is integration by parts, like I said on this, where, let's see, u is equal to f of x dx. So like I said, u is equal to f of x. And then that makes du equal to f prime of x dx. And then dv will be equal to dx, which means v is equal to x. So that's our setup for integration by parts on this integral right here. Then let's just recall the integration by parts formula will give us VU evaluated at the endpoints minus the integral of V du. Of course, where that's a definite integral on those same bounds. Okay, so anyway, let's get to it. This is going to give us the limit as n goes to infinity. And then we've got this multiplier of n out front. And now we'll have u times v, so that's going to be x times f of x evaluated from 0 to 1 by n. And then after that, we'll have minus the integral from 0 to 1 over n of, let's see, x times f prime of x dx. So we've got something like that. But now we're going to use an assumption about f prime, which we haven't talked about yet. And this, like I said, is really just done so that we don't have to dive into just some more niche topics like the mean value theorem for integrals. And what we'll assume is that f prime is bounded. And let's say the absolute value of f prime of x is less than or equal to m when x is on the interval from 0 to 1. But let's see what that means. That means that the absolute value of this integral will be pinned between 0, and I'll just put absolute value of this integral right here with the box so that I don't have to rewrite the whole thing, and then it'll be pinned above by m times the integral from 0 to 1 over n of x dx. Okay, great. And then let's maybe multiply through by the n just so that we have it. But now notice that that integral is very simple to calculate. That will give us m over 2 times n. The 2 comes because we've got x squared over 2, and then that would give us an n squared in the denominator, but that cancels with this n in the numerator. But now since m is fixed and n is approaching infinity, that means that this bit will go to 0, which means that this bit goes to 0 under our limiting procedure. Okay, so let's see, that's going to leave us with the following limit to finish us off. We have the limit as n goes to infinity of n times 1 over n times f of 1 over n. Okay, nice. But n times 1 over n is clearly equal to 1. Then if we take the limit as n goes to infinity of f of 1 over n, we get f of 0 as needed. So just to connect the dots, we started here and we ended with f of 0, which was our physicists' defining property of this delta function. Okay, so let's try this one more time, but now with a continuous function. Okay, so for our next go at this, like I said, we're going to do this with a family of continuous functions. And those continuous functions will be delta n of x, which is equal to the square root of n over pi times e to the minus nx squared. And then of course delta x will be that limit. So this gives you something that is smoother but still has this spike action happening at the origin. So in particular, we get something like this, where this thing is getting thinner and thinner and thinner as n gets larger and larger and larger. It gets thinner and higher. So you can graph a couple more copies if you'd like to. I'm sure you could do that in Wolfram Alpha or something. Okay, so now let's get to proving a certain calculation which will essentially help us get this result right here. And it starts with something very, very easy, and that is the integral from minus infinity to infinity of delta n of x times x to the 2m plus 1 dx is immediately equal to 0. We don't have to do any calculation right there. And that's because we have an odd function. So this is an odd function. We're integrating over a symmetric domain. Anytime you do that, you get 0. I guess like really what we need is that this function dies off like asymptotically, but it does because exponentials always win over polynomials. Okay, so that's an odd function, so we get 0. I guess like we can really see this is an odd function because this delta nx is an even function. Okay, but what about the even powers of x in here? So let's make that calculation. So let's do the integral from minus infinity to infinity of x to the 2m delta nx dx. So that's going to give us the square root of n over pi times the integral from minus infinity to infinity of x to the 2m times e to the minus nx squared dx. Okay. Now there's a couple of ways to calculate this. Notice this looks fairly similar to the Gaussian integral. In fact, if m is equal to 0, this is really similar to the Gaussian integral, and that's what we'll actually use at the end. But then let's also notice that if we take the derivative of this exponent with respect to n, an x squared pops out. So it really looks like we've taken the derivative of this thing with respect to n m times. That would have an x squared pop out m times, which would give us x to the 2m. Okay, so let's collect that with the following statement. This is the square root of n over pi, bringing this down. We have the integral from minus infinity to infinity. And then we'll have minus 1 to the m, because notice a minus sign comes down at each step as well. We need to counteract that. Then we have the mth derivative with respect to n of e to the minus nx squared dx. We've got something like that. But now let's notice that we don't have a power of x anymore, which is nice. Let's also bring the derivative outside of the integral, which is a bit sketchy without saying that we can do it, but everything is okay in this case and we can do that sort of action. Okay, so that's going to give us a minus 1 to the m outside, and then we'll have the derivative with respect to n m times of the integral from minus infinity to infinity of e to the minus nx squared dx. And now this guy right here is related to the Gaussian integral. It's not exactly the Gaussian integral because we've got this multiple of minus x squared up there, but it's related enough that a simple substitution will take us from one to the other. And we're not going to do that substitution because it's fairly well known. We'll just take the known value for an integral like that. Okay, so bringing things down, we have minus 1 to the m, and then we'll have the square root of n over pi, and then we'll have the mth derivative with respect to n of the square root of pi over n. So that's the value of that Gaussian integral. Maybe let's put an overline of that in magenta so we see exactly where it came from. Okay, but now we can do a bit of simplification. Notice this pi cancels with this pi, and then we can rewrite this in a format that is more suitable to taking repeated derivatives. So I'm going to have minus 1 to the m, and then we'll have the square root of n, and then that same crazy looking derivative, and then we'll have n to the minus half power. Okay, so now let's make that calculation. We'll have minus 1 to the m, the square root of n. Now the first derivative will give us a minus half out front. But then the second derivative will give us a minus 3 halves, the third derivative a minus 5 halves, all the way down to the mth derivative will give us a minus 2m plus 1 over 2. And then we'll be left with a certain power of n, and that certain power of n is n to the minus 2m minus 1 over 2. So that's doing the power rule over and over and over and over and over again. Okay, we're running out of room, but before we move on, I'd like to notice that we have exactly m factors here, which means there are m factors of minus 1 that we can use to cancel these m factors of minus 1. So all of these will cancel to pluses, and then that'll swap as follows. Okay, so now let's bring that up, and then we'll do the final steps. So this is where we left off. So now I'm going to take this last term and rewrite it just a little bit before we get to simplifying. So let's notice this last term will turn into, let's see, 1 over n to the m times the square root of n. So that's just by some straightforward simplification. But check it out. Now this square root of n here will cancel this square root of n here, and then we're able to write this in a more closed form. So let's notice that this will be 1 times 3 times 5, ending at 2m minus 1 in the numerator. In the denominator, we'll have 2 to the n times n to the m, so that'll be 2n all to the power of m. But now let's notice that if we apply our limit as n goes to infinity, two different things happen. So if m is equal to 0, we simply get the number 1. But if m is bigger than 0, we'll get 0. That's because if m is bigger than 0, we've got a power of n in the denominator, which is going to overtake this large product which is in the numerator. Notice we're fixing m and then taking the limit as n goes to infinity. So that's what we get right here. Okay, so now let's put this information together to get this result. Okay, so these are the two results that we came up with. Now we're going to take our function and write it with its Taylor expansion centered at 0. So I guess that is its Maclaurin expansion. And this may seem problematic because what if the radius of convergence is not infinite? We're about to take an infinite integral. Well, I think that's okay because this function right here will really kill off any of the divergence which might happen outside of the radius of convergence. As long as f of x is one of these classes of functions that doesn't grow too fast. Okay, so let's rewrite f of x as the sum as n goes from 0, or maybe we'll say m goes from 0 to infinity of a sub m x to the m. And then let's split this into even and odd parts. So we can have this is the sum as m goes from 0 to infinity of a sub 2m x to the 2m plus the sum as m goes from 0 to infinity of a sub 2m plus 1 x to the 2m plus 1. Okay, and then for our final calculation, we have the integral from negative infinity to infinity of f of x delta x dx will give us the limit as n goes to infinity of the integral from minus infinity to infinity of the sum of the even part. So this is going to be the sum as m goes from 0 to infinity of a sub 2m times x to the 2m times delta n of x dx. And then we've got the odd part as well. So that's going to be the integral from minus infinity to infinity, and then we'll have the sum as m goes from 0 to infinity of a sub 2m plus 1 x to the 2m plus 1 delta n x dx. Great, so we're left with something like that. But now over here, just applying our integral without applying our limit, by this rule right here, we'll see that this turns into 0 because we're integrating this odd power of x times our delta n. So like I said, that's going to go to 0. But then by this limit right here, almost all of these terms go to 0. All of them except for the m equals 0 term. And so that's going to leave us with a sub 0, well, times the number 1, but a sub 0 is just a constant. But let's recall that by the Maclaurin expansion kind of formula, a sub 0 is exactly f evaluated at 0. So that finishes off this, like, albeit sketchy calculation. But just because it's sketchy doesn't mean it's not illuminating of how the process goes. And that's a good place to stop. Thanks for watching and sticking around until the end of the video. And since you're here, don't forget to gently press that like button, subscribe, ring the bell, and select all notifications to never miss a video. If you want to get your name in the credits like you see here, access the live seminar series, review videos before release, and more, go to patreon.com/michaelpennmath and become a Patreon member today. If you want full ad-free course content, subscribe to my second channel, Math Major. I've got courses on linear algebra, complex analysis, and proofwriting, among several others. And that's everything. Bye.